This is not a scene in a horror film or me trying to scare you. This is just a trick of how electricity can frighten us, brighten our day, or even entertain us. The strobe lights in a disco, or the Christmas lights on the streets, or in houses, all these are magnificent effects of how lights work through the presence of electricity. Today, we will uncover the science behind how electricity flows and how it can power up all the lights and other electrical gadgets that depend on it. This is Teacher MJ, and this is DepEd TV. In our previous lesson about heat and temperature, we learned that heat energy flows from a body with higher temperature to a body with lower temperature. The flow ceases when both bodies reach the same temperature. Similarly, when an electrical conductor is connected to different electric potentials, charge flows from one end to the other end of the conductor. Without a potential difference, no charge flows as well. To attain a sustained flow of charge in a conductor, an electrical setup must maintain a difference in potential while charge flows from one end to the other. These charges are free electrons that would only flow in conducting wires usually made of metals and connected to a voltage source. When there is a flow of electric charges, an electrical current is present. Specifically, the terms electric current, voltage, and electric resistance and their relationship with each other will be our main discussion points for today. But before we get into that, it's time for a drill. Before we proceed, let's try to test your knowledge about our lesson by answering these questions. Let's do this, Sci folks! It is a difference in electric potential energy in joules per coulomb. A. Circuit. B. Current. C. Resistance. Or D. Voltage. The correct answer is D. Voltage. What is the SI unit of voltage? A. Ampere. B. Ohm. C. Volt. Or D. Watt. The correct answer is C. Volt. It is the number of charges passing through a wire per unit time. A. Current. B. Power. C. Resistance. Or D. Voltage. The correct answer is A. Current. What is the SI unit of current? A. Ampere. B. Ohm. C. Volt. Or D. Watt. The correct answer is A. Ampere. It is the opposition to the flow of electric charges as they travel through a conducting wire. A. Circuit. B. Current. C. Resistance. Or D. Voltage. The correct answer is C. Resistance. Did you get all the items right? If not, don't worry, because at the end of this week's lesson, you will surely understand all the things you need to learn. So let us now begin exploring basic electricity. Electric current is the rate of flow of electric charges from one point to another in a circuit. It is measured in amperes. 1 ampere is a rate of flow equal to 1 coulomb of charge per second. Basically, the current is caused by the movement of electrons. Mathematically, electric current is given by I equals Q divided by T, where I stands for the current in amperes, Q, charge in coulombs, and T, time in seconds. A sustained current in conducting wire requires a suitable pumping device, meaning charges will flow only when they are pushed or driven. The work needed per unit charge to move between 2 points is called voltage, expressed in volts. Voltage is what makes an electric charge move. It is a difference in electrical potential energy per unit of charge between 2 points. Simply put, it behaves like a pushing force, forcing electrons to start moving around, which creates an electric current. When the voltage is increased to 3 volts, notice that the blades of the fan turn faster. This time, let's supply it with 10 volts. You will see that the blades of the fan is turning even faster. Why? Because there is now a bigger pushing force allowing more current flow. Mathematically, voltage is given by V equals W divided by Q, where V stands for voltage in volts, W, work in joule, and Q, charge in coulomb. A common automobile battery will provide a voltage of 12 volts to a circuit connected across its terminals. Then 12 joules of energy are supplied to each coulomb of charge that is made to flow in the circuit. Remember, voltage does not go anywhere. It only drives the charges to move. This figure is the electrical circuit symbol of a battery. You will notice that this has pairs of short and long lines that represent negative and positive terminals respectively. We know that batteries and generators are the primary sources of electric current in an electric circuit. How much current exists in a circuit depends not only on the voltage but also on the electrical resistance of the conductor. Electrical resistance is the opposition to the flow of current by the conducting wire. The electrical resistance of the wire depends on its thickness, length, and conductivity. Thick wires have less resistance than thin wires because thick wires have a greater cross-sectional area for the electrons to flow through as compared to thin wires. Longer wires have more resistance than shorter wires because longer wires have longer path for the current to flow. Copper wires have less resistance than steel wires of the same size because copper has higher conductivity than steel. Conductivity is the property of matter that allows current to flow. The higher the conductivity of the material, the more electrons can freely flow. Electrical resistance also depends on temperature. Atoms violently vibrate at higher temperatures, which result in greater collision, creating more resistance against the flow of current. Electrical resistance is measured in ohms, named after George Simon Ohm, with the Greek letter omega as its symbol. An electronic device that is designed to resist the flow of current is known as a resistor, with its equivalent electrical symbol. A resistor can also be a light bulb with its equivalent electrical symbol that will convert the energy that is moving the electrons into heat and light. The relationship among voltage, current, and resistance is summarized by Ohm's law, which states that the amount of electric current is directly proportional to the voltage applied to the circuit and inversely proportional to the resistance of the circuit. George Simon Ohm discovered that at constant resistance, electric current in a circuit is directly proportional to the voltage. To understand that, take a look at this. For given values of resistance, current, and voltage in picture A, Current will double if voltage is doubled at constant resistance as shown in picture B. This means that the greater the voltage, the greater the current. If the resistance of a circuit is doubled, the current would be reduced to 1/2 when voltage is held constant. In a simple circuit, voltage is directly proportional to current. Its proportionality constant is R equals resistance. V equals I multiplied by R, where V stands for voltage expressed in volt, I stands for current expressed in ampere, and R stands for resistance expressed in ohm. Now let us try some problem-solving activities involving Ohm's law. Example number 1. Find the resistance in ohm of a single motor horn if it has a voltage of 6 volts and current of 2 amperes. For the given, we have voltage at 6 volts and current at 2 amperes. Required resistance. For the solution, we have to use Ohm's law. V equals I multiplied by R. We have to divide both sides by current. So V over I equals I multiplied by R over I. R equals V divided by I, that is 6 volts divided by 2 amperes. And that gives us 3 ohms. Example number 2. If a circuit has a resistance of 40 ohms and a current of 5 amperes, what is its voltage? For the given, R is equal to 40 ohms and I is equal to 5 amperes. Required voltage. For the solution, we have to use Ohm's law. V equals I multiplied by R, and that will bring us down to 5 amperes multiplied by 40 ohms. That will give us 200 volts. Example number 3. What will happen to the current if the resistance is tripled? State the relationship of current and resistance based on your answer. V equals I multiplied by R. So originally, I is equal to V divided by R. If R is tripled, then I equals V over 3R equals 1 over 3 V over R. Therefore, when resistance is tripled, the current is reduced by 1/3. The result shows that when resistance is increased at constant voltage, the current is reduced. Wow! That was a lot of numbers. I hope you could remember all those. Before we proceed, let's recall the symbols related to the Ohm's law. Let's see if you can remember. What does this symbol represent? Right, resistor. What about this one? Correct, bulb. What about this next symbol? Awesome, battery. Now that you have learned the relationship of electric current, voltage, and resistance through Ohm's law, it is now time to check your understanding. Again, you write your answer on your notebook and we will check it right after the assessment. You have 5 seconds to answer each item. So, let's begin. What is the electric current of a circuit that has a resistance of 100 ohms and voltage of 12 volts? A. 0.12 amperes. B. 9 amperes, C, 12 amperes, or D, 25 amperes? The correct answer is A, 0.12 amperes. What is the electric current of a circuit that has a resistance of 100 ohms and a voltage of 6 volts? A, 0.06 amperes, B, 4.50 amperes, C, 6 amperes, or D, 12.5 amperes? The correct answer is A, 0.06 amperes. What is the voltage of a circuit that has a resistance of 6 ohms and a current of 2 amperes? A, 9 volts, B, 10 volts, C, 11 volts, or D, 12 volts? The correct answer is D, 12 volts. What will happen to the current if the voltage is reduced to 1/2? A, tripled, B, doubled, C, decreased by 1/2, or D, decreased by 1/4? The correct answer is C, decreased by 1/2. What type of conducting wire has the greatest resistance to the flow of current? A, thin long wire, B, thick long wire, C, thin short wire, or D, thick short wire? The correct answer is A, thin long wire. You did a wonderful job for this week. Congratulations for completing another activity filled with challenging experience. Catch our next episode next week and you'll be in for a lot of learning surprises. This is your teacher MJ, your partner in exploring, discovering, and enjoying life. This is DepEd TV.